Let's try an example of a two-dimensional collision. Here we have a 15-kilogram car that is moving in the east direction. So we'll label it. It's traveling east at 25 meters per second. Now this car is going to collide with a van that's coming north. So here's our van. And this van is 2,500 kilograms. And it's moving north at 20 meters per second. What's going to happen is once these two objects or cars collide, the wreckage is going to be assumed to undergo a perfectly inelastic collision. In an inelastic collision, that basically means that these two cars are going to be sticking together. So after the collision is over, these cars will probably end up moving, maybe something like this, as one big mangled chunk of metal with a larger or combined mass. Now they're going to end up moving off at some angle theta to the horizontal or the east direction, and they're going to move off at some final velocity. We want to find these two variables. Basically, these are the variables that would define the direction of the wreckage and the velocity of this wreckage. So as we set this up, we need to consider that in a two-dimensional problem, we really need to isolate x and y directions separately. So if we sum up all of the initial momentum in the x direction, we'd find that really only our yellow car here is moving in the x direction initially. So we could take its mass times its velocity, and there's our initial momentum in the x direction. In the y direction, we could sum up the initial momentum in the y direction. And again, we'd realize that only one of these cars is actually moving in the y direction. That would be the van that we have over here. And that van has a mass of 2,500 and a velocity of 20 meters per second. So what we have is initial momentum in the x and initial momentum in the y. What I want you to realize is that, again, momentum is going to be conserved. So that means that if we look at our initial momentum in the x direction, it has to be equal to our final momentum in the x direction as well. Now, because our final momentum is off at some angle theta, what we need to do is look at what component of this final momentum is actually in the x direction. If we look at that final component of what's in the x direction, we would have the total mass, or the 2,500 plus the 1,500, to give us a total of 4,000 kilograms. And it would be moving off at some velocity, vf, but the x component of that velocity would really only be the vf cosine of theta. So we'd want to look at the x component of that final velocity. The same thing goes for the y direction. In the y direction, the initial momentum has to be equal to the final momentum. The final momentum in the y direction is going to be the large mass of both cars stuck together, and only a y component then of this final velocity. So basically a vf sine of theta is going to define the final velocity in that y direction. What we want to do then is to simplify these equations a little bit. So in simplifying these equations, we really want to solve for one of the variables so that we can plug it into our other equation and begin to actually solve these simultaneous equations. I'm going to come up to the very first equation and simplify it just a bit. When I take the 1,500 times the 25, I get about 37,500 equal to the 4,000 VF cosine of theta. Dividing by the 4,000 and the cosine of theta, I essentially am isolating VF so that I get about 9.375 divided by cosine of theta equaling my VF. So when I come to my second equation, I can simplify this a bit as well. The 2,500 times 20 gives me 50,000. And I can now plug in what VF is. VF is 9.375 divided by the cosine of theta. And then I'm multiplying this by the sine of theta. So I can take the 50,000 and divide it by the 4,000 and get about 12.5. Just to simplify this a little bit further. And what I want you to recognize is that as we begin simplifying this further and further, and take our 12.5 divided by our 9.375, we can simplify this even further and bring that over to this side where I'd get about 1.33 when I divide out the 9.375. Well, I want you to recognize that what's left on this side of the equation is basically a sine over a cosine. And sine over cosine is equal to the tangent of the angle theta, and now we can solve for our theta. Solving for this, we get theta equal to just over 53 degrees. Once we know what theta is equal to, then we can come back to either one of our original equations, plug in a value for theta, and then solve for VF. Why don't you go ahead, pause the video, try going back to either the x or the y direction equation, plug in the value of theta that we now know, and see if you can solve for that final velocity of these cars. When you plug those things in, you should get about 15.6 meters per second. Now we know everything there is to know about the final velocity of this wreckage. It's moving at 15.6 meters per second at an angle of about 53.1 degrees from the east direction.